Welcome back to Bio 6612. In this week's lectures, we're going to talk about marginal models, which are an alternative to linear mixed models for analyzing longitudinal data. I have a couple optional readings here, which will give you some more perspective on marginal models. The first is more applied look. Agresti will give you more in-depth theory on these models, and then a couple other resources as well. So we've talked about mixed effects models already, which are basically generalized linear models for longitudinal data that where a subset of the regression coefficients vary from subject to subject, and that captures the correlation within subjects and longitudinal data. And we've talked about that for continuous data at this point, and next week we'll discuss how to apply those types of models to count and binary data. But this week, we're going to focus on marginal models, where the basic premise is to make inferences about population averages. And they focus on estimating the fixed effects and variance matrices, but don't introduce subject effects like linear mixed models do. And the interpretation for these models is analogous to cross-sectional models. So yeah, the focus of marginal models is on inferences of population averages. They separately model the mean responses and within-subject association across repeated responses. Marginal models do not require joint distributional assumptions for vector responses, which may be difficult for discrete models. Instead, you just provide the mean and the variance. So in a sense, these are like methods of moment estimators applied to models for longitudinal data. And the avoidance of making distributional assumptions for the full data lead to a method of estimation called generalized estimated equations, which is, or GEEs, which is sort of a synonym for marginal models. So in marginal models, we equate the marginal expectation of the response. This expectation is called mu, which depends on the covariates through a known link function in a GLM-like framework. So this is sort of high-level look at what that model looks like, where you have your mean of your outcome, mu ij, some link function that links the response to the covariates, and the link function functions in the same way as it did when we were looking at GLMs, and then your set of linear predictors, your x's and your betas. We also provide marginal variance of y, which is a function of both the mean and some scale parameter, and something that we'll have to specify in these models. And then we also have to specify the within-subject association among the responses, which was a function of the mean and additional parameters, say rho, the correlation, that have to be estimated. So just a quick comparison to GEEs versus the GLMs that we've worked with earlier in the semester. The GEEs have a very similar model specification framework to GLMs. The main difference is that we don't explicitly specify a distribution for our data, but we do have to explicitly specify some kind of correlation structure for how responses are correlated in time. So GLMs, the way that we specify a GLM is using these three components: the linear predictor, your x beta, as well as a link function, that's your g, which is logit or maybe the log, depending on what your data is. And then your data distribution, that's, maybe y has a Poisson distribution if you're looking at count data. For GEEs, you have the same linear predictor, your x beta, that you have to specify. what betas and x's that you want to consider. You also specify a link function that's going to be the same type of links functions that we've been using. And the link function that you choose sort of dictates the mean structure of your data. We also specify a variance. So since we're not just specifying a data distribution explicitly for the whole joint distribution of your outcome, you have to specify a variance as well. Though often we use variances from exponential distributions, exponential family distributions. Depending on the type of data that you're working with. And then the final piece that we have to specify that isn't present at all in normal GLMs is this correlation structure between Y's on the same subject. So the correlation structure that we specify in GEs is referred to as the working correlation structure. So since we don't know the true correlation between different time points for our data, we want to guess at this structure for the sake of our modeling. And EDA or exploratory data analysis can help with this. But some of the most common correlation structures, which are also referred to in more detail in lecture 10.3, are independence, which is no independence between time points. All observations are considered independent. That's the same assumption you make in your ordinary least squares, a regular GLM. Exchangeable correlation structure, which is the same correlation between any two time points. That's when you have your correlation matrix will look something like this, and you have just the same correlation parameter row at all time points. There's autoregressive, in which visits closer in time are more correlated. And we discussed the Toeplitz correlation structure as well in that lecture, which is a generalization of the autoregressive structure. So at a high level, let's talk about the continuous response. So for the continuous response, or normal data, our model would look like expectation of Yij equals Xij beta. You don't have a link function. The link function is the identity link. So for our continuous response, we have a linear regression-like structure for the mean. We would specify a variance to be some sigma squared j, different variance at different visits, but the variance doesn't depend on the mean. And that's the same assumption we make for normally distributed data in general. And then we also have to choose some sort of correlation structure. In this case, for one example you could use is an autoregressive correlation structure, though of course you could choose other correlation structures as well. And the structure you choose is going to depend on your data. High-level example for count response. For the mean structure, we would choose the log link, like we did for regular GLMs. This is a Poisson regression type link. We might choose Poisson variance as well. So the Poisson variance is equal to the mean. And then we might specify an over-dispersion parameter depending on whether we think our data is over-dispersed. And then we specify a correlation structure. And we have the same choice of possible correlation structures here as we would with continuous data. And another common type of response for GEs is a binary response. And a common specification might be the logit link for logistic regression on longitudinal data. And then we would choose a Bernoulli variance and we place a correlation structure on that as well. And unstructured correlation means that you have a different correlation at every single combination of time points. This is the correlation structure that estimates the most correlation parameters. However, in practice, this is not used very often, even though it's the most flexible, because it can take a lot of data and computation time to actually estimate unstructured correlation. So one of the really nice things about GEEs is how you interpret the model parameters. The regression parameters are really interpreted in a very similar way to how you would interpret a non-longitudinal GLM. They have a population average interpretation that is analogous to a cross-sectional model. And we'll see some examples of that in subsequent lectures. And the way that GEEs are actually estimated is using what's called quasi-likelihood estimation. And this is because GLMs, even though GLMs assume a certain distribution for the response vector y. Say y has a Poisson distribution with some mean mu. That would be one common specification. And GEEs, while you do tend to use exponential family lengths, we don't explicitly assume a certain distribution for our data. We just take the mean and the variance, the first and second moments, from common exponential family distributions. But because we're not explicitly assuming a certain distribution for our data, we don't have a true likelihood for our data. Instead, what we'll have is a quasi-likelihood, which is defined by the mean and variance that we specify. And because we have a quasi-likelihood, we can't use a true maximum likelihood estimation to estimate the parameters. Instead, we have to use quasi-likelihood estimation. And the way that quasi-likelihood estimation works at a high level is that parameter estimates are obtained by solving the score equations of the quasi-likelihood. And a representation of the score equations are given in this equation here, where you'll have a score equation for each of the betas. This is a bold beta, meaning this is a vector of your beta parameters. And that score equation is going to be made up of the derivative of the mean structure with respect to your betas, as well as this variance covariance matrix, which incorporates both the variance you specified as well as the correlation you specified. So it's going to depend on your selected covariance structure, as well as your data, which is incorporated into that estimation as well. So because of the way that the score equation is written out here, what this means in practice is you're going to use this to solve for your betas, which means that your betas are going to be a function of the mean structure you specify, as well as the variance you specify, and the correlation structure, as well as your observed data. The score equations of the quasi-likelihood that I provided in the previous slide are called estimating equations. And these are typically solved using an iterative algorithm, something like iteratively weighted least squares. And there is asymptotic large sample theory to show that estimates for beta are unbiased as your sample size goes to infinity. However, as I referred to before, the quasi-likelihood is not a true likelihood function, and for that reason, inference is a little bit different in GEEs than it would be in GLMs. So inference methods based on the likelihood function don't apply. And this means that AIC and BIC and traditional like model fit tests that compare your model to some saturated model under the likelihood assumptions won't work. However, there is an alternative called quasi-likelihood under independence model criterion, or QIC, which can be used in place of something like AIC or BIC to compare between different nested and non-nested models. So as I mentioned, the betas that you estimate are going to depend on the variance, mean, and correlation structure you choose. So this means that we have to pick a correlation structure for our data in order to estimate the betas. However, what if you don't pick the right correlation structure? Well, in GEEs, we have both working and robust standard errors. So the working standard errors come from the working correlation structure you choose. Working means working correlation structure. And if you don't choose the correct working correlation structure for your data, you'll still get betas that are going to be estimated consistently. You'll still get betas that are unbiased, even if your working covariance structure is wrong. However, the issue is that your inference, your standard errors, might be off if you have the wrong working correlation structure. Luckily, there's sort of a fix for this that's built into the GE estimation framework called robust standard errors, which come from something called the sandwich estimator. And what the sandwich estimator does is it takes your working correlation matrix and it sandwiches it between empirical covariance estimates based on the empirical residuals that approximate some underlying covariance structure in your data. And so what happens is you specify a working covariance structure, but then the GEE output will also return a robust standard error based on the sandwich estimator and your working correlation structure that will give you better estimates for your standard errors. And what's nice about this is under ideal conditions for the sandwich estimator, this estimator estimates your variance in a way that is robust to misspecification of the correlation structure. So you'll get standard errors that are still going to be appropriate as long as the ideal conditions for the sandwich estimator are satisfied. So what do I mean by ideal conditions? Well, that means that the number of observations per subject is a lot smaller than the total number of subjects in the data set. It also means that your data is relatively balanced across time and covariates, and you don't have too many missing observations, and you have a similar number of observations per subject. So basically, balanced data with little or no missingness. So what type of inference is typically used for GEEs? Wald-based tests are the most common, and that's because LRT tests will not work because of the quasi-likelihood that rather than the true likelihood function. And for the Wald-based tests, the standard errors for these tests come from the sandwich estimator rather than the working covariance structure. And though these are robust to misspecification of the working correlation structure when the ideal conditions for the sandwich estimator are met, the estimates will be a little less efficient if you don't choose well. So in general, it's good to think about your working correlation anyway. And then model checking for your GE can be carried out by examining the residual plots. And finally, I want to touch on some of the GEE limitations. But some of which have been discussed briefly already. But basically, because GEs all use quasi-likelihood estimation, maximum likelihood estimation tools won't be appropriate for testing fit, comparing models, and conducting inference about parameters. Another limitation is that GEs, unlike LMMs, will not give subject-specific estimates. They will only give population-level estimates. These models perform poorly when the data is very imbalanced or you have a lot of missingness. And they also perform poorly when you have a lot of observations from only a handful of subjects. In the next set of lectures, we'll look at implementing some of these models in R for continuous binary and count data.